And so the idea here was just not a particularly long talk, but just something like, okay, here's my problem. This is what I'm trying to do. And this is what I'd like to do, and we'll just kind of capture that. So probably the easiest way would be if people have got their got some talks. If you could just put them, we'll just transfer them to this computer here, and then you can use this to actually do the presentation. And then we'll also have captured your slides at that point. So who would like to lead off? Sure, perfect.
One thing I just want to show real quick is what we're actually doing. I showed this briefly yesterday, but what we're doing with the presentations and how we're showing things. This is all through the blog that we've been writing. So if you come to the disk page, there's a blog here. And so with each location, we've got a short write-up just about the day, and then there's also a short write-up for each presentation that's been done, and we post the slides along with that. So if you're willing, we will, and if not, then we just won't post your slides. There's no problem there. Just let us know what you prefer. And so with that, come on up. Thanks.
You know what, that tends to be a heavy size file there.
Okay.
40 megs. But maybe I can then send you a PDF.
Oh, sure. Yeah. And so here, presenting, this is change your slides, or you can use the keyboard, whatever you prefer. And then
that's too difficult.
So, whichever you like.
Okay, ready? Yep. Well, my name is Hector, and I work for GRS as a geophysicist. We are the well, I would like to start the this brief talk showing a picture of the field guys that are the ones that acquired the data for us and now like our heroes. Here's Adrian. He's our manager for operations. So, well, that's kind of the terrain conditions that we used to survey. Okay, so I'm going to talk to you briefly about. Well, first, in order to put you in some context about the GRS tree correction IP data acquisition, I will try to do it in three slides. That's pretty much, but I'll try to do it. And then I will show you an application of our data to mineral exploration, case history for Australia, and then some summary, some discussion about what is the problem that we are facing currently. Okay, so well, GRS. This was a pole dipole survey. This is data that actually we acquired here in Chile with a 200-meter dipoles. In this case, I'll show you an example between where the TX current injection and the receiver, it's around 3 kilometers apart, and an M equals to 15.5 or something like that. And we also have a remote station that we use for two different purposes. One is for as a remote reference for the MT in order to reduce some some non-spatial correlated noises. So, well, in the morning, I'm pretty sure you remember that Doc show us like how is the wave that we inject to the ground. That's a square wave, but actually the wave that we receive hardly ever it's as that. It's something more like this. So this is has a lot of different kind of noises on it, and we are mainly concerned in this kind of behavior and everything that deviate the decaying curves. So in order to clean the data, we need something. We need to do something about it. So what do we do? sorry, we apply a Telluric correction for this. Okay, so we calculate how's the E field that the natural currents are, how the natural currents are in the field that we are working on. And for that reason, we start with the IP, the empty transfer function. That's the thing that we first acquire when we are working at EC in a Telluric corrected data acquisition. And then we convolve this with what we acquire as a B fields in the remote stations. So when we perform this convolution, what we obtain is the the EX fields on the field. So it's a calculation, and you can see it here. That's the Telluric noise that we calculate from the convolution between the B field and the Telluric transfer function. So then we can perform a subtraction between those time series, and that's what we obtain. So that's more like the thing that we see this morning, right? With something that's like pretty clean square wave. So this is a full duty square wave. You see, only positives and negatives, no off time. But one particularity of the Mindas data is that we record the current that we are injecting into the ground with a high precision, so we can go from one way to another with the system response that we calculate for each of our receivers. So it's pretty easy to us to work in time domain or frequency domain. It's a matter of what are the problems that we are trying to take on. So, okay, this is the Telluric correction. So now when I show you some pictures of the Telluric corrected data, you don't now have in mind what I'm talking to. So, well, this is the decay that you would expect if you were working with data without Telluric cancellation. It's pretty noisy. Those are the cold decays, and this is the off time when you cut off the current, and you expect to see how that data decays, and that's what actually you are measuring. Where you are measuring your IP response, right over there. It's the area under the question. And these are the cold decays. That's a theoretical behavior of the of a chargeable body. Okay, so I don't know if you can look at it, but the chargeability for this example is around 3.1, but the error of that data it's 130%, pretty high. But then when we apply the Telluric correction, we obtain something much cleaner. So now we have a value of 2.5 and an error of 15%. So much more reasonable to work with. Okay. So now, with that briefly, well, you can ask me wherever you want then about the Mindas data. But now I'm going to talk to you about this project that Terry that was here yesterday, and Peter Ralston, our principal geophysicist, developed for Olympic Dam. And using our data, we perform a control source EM inversion in order to tackle something that at that time was a very difficult IP problem. And now I'll tell you what. So what we have here is the DC resistivity model and the empty resistivity model for the line that we measure in Olympic Dam. It's a 5-case line with measured with pole dipoles, measured as pole dipole survey. And the thing is that here we have a shallow conductor well depicted by the empty data, not so well depicted by the DC data. So the thing is that you can expect some reasonable amount of EM coupling if you have a chargeable body over here, or if you have an IP response, you may take on consideration that you may be facing with some EM coupling contribution to that body. So we need to what the theory says about this is that in order to avoid the EM coupling, we need to measure with low frequencies. But the problem is that at the moment that you start surveying with low frequencies, you start putting more into your survey the telluric noise. So in order to remove that, you need to apply a telluric cancellation, and that's what we did at this time. Let me show you briefly this is for those that are skeptical about the empty resolution of the model. This is the basement plotted through some drill holes that we have here. And you can see that what the peaks is pretty consistent with what they log. This is the shale layer that's around plus or minus 100 meters. Okay? And this is in wood in a tremendous good agreement in top and bottom extension of the of that cover. Okay. So this is a picture of the what do we see at that time for the chargeability anomaly. You see? So we need to assess if this is a real IP anomaly or if this is caused by EM coupling. So that's part of it. And well, for that reason, as I told you before, the meanness data allows you to go from time domain to frequency domain. So what they did at that time was to take the first harmonic of the wave that you were introducing to the ground, and the two first, so the first harmonic and the next following harmonics. Actually, you're using 3 harmonics of the square wave. It's a square wave of 0.048 hertz, around 5 times of current. We invert that as a control source EM problem for amplitude and for phases. And the amplitudes agree pretty well, but what happened with the phases? Okay, sorry, I'll talk to you right now about what happened with the phases. This is the a single section of primary resistivity and the observed chargeability for that line. So for those of you that are not so familiar with this is pretty clean data. If in the future someone presents you something like this and you are in the position of a mineral exploration company in a mine, this is have in mind that this is really good quality data. Okay. So this is the pole-dipole array, and this is the dipole-pole array. So here's where probably your anomaly lives. You see, and probably these negative values are caused by EM coupling. So among the things. Okay. So we performed the control source inversion, and I told you that the amplitude fits very well. But what happened with the phases? That phase cannot be fit. Can solve IP. The software that we use at this moment can solve IP. It's just an EM code. It's a code based on. It's a code that developed the scripts in the script institution of oceanography. So it's called Maritime. And what we found here is that the biggest phase misfit were around the hover body. Okay, so right over here. So the tricky thing about this problem is that you need to acquire really good quality data, and particularly when you move to the frequency domain to have good quality of the phases. And that's a pretty difficult problem. We have tried to apply this very similar approach to data from Chile, and the results that we have obtained at the moment are not so successful due to that the response in the phases are too small. So it's difficult for us to determine if the anomaly in particular is caused by EM coupling or IP. Okay. So now I'll need just a quick summary about this. Reposing the service as a control source, EM makes EM part of the solution and not part of the problem. So this is kind of a different approach. It's not applying the EM decoupling to the phases as we saw in the morning. We use the EM data that we have in our time series, and we try to see how well we can model it and see the difference that we observe in the EM response and in the IP response. So the evidence that observes some modeling that I do not have here, but is that you can use data up to 1 hertz and still having a good IP response on that phases. So that's pretty good because if we increase the frequency that we are in, the frequency of the current, that the waveform that we are injecting, that means that we can survey that, we can acquire the data quite faster than in the case that we are using some lower frequency. Well, this problem that I show you what used to be a hard problem to tackle, but now we have with this software and using this approach and making sure that we have good faces, we can some way discriminate between if that response is just an EM coupling or an IP response. But what we observe now is that we can look way deeper and over more conductive cover, and it's not so easy to now to discriminate which response belongs to which word. Okay. So, well, that's now if you have any questions, wait, thanks for your attention.
Thank you.
Okay.
Any questions?
So of all of the things that you mentioned, you actually did go through quite a bit of stuff. What's the most well-defined problem that if one could tackle that it would make a difference?
Well, I think the most important thing is that you need to acquire high-quality data and in order to assess the good faces. If you have good face measurement, you can, I think, make more easier discrimination between EM and IP. But that's it. Sometimes difficult regarding terrain conditions we are observing, and actually taking account that you are surveying larger voids that are way deeper than they used to be as the previous. I don't know. I answered your question.
Well, I'm just trying to get a grasp of like what the biggest return is for time spent on something like this. Where is the weak link in the chain? Are you acquiring data then with different lengths of duty cycles?
No, we use half duty, full duty waves.
Full waveform.
Yeah, full duty waveforms, and then as we calculate, as we have a precise measurement of the current that we inject of the waveform, we can easily get a system response for that, and then calculate for instance, how a half-duty wave will look. Just a simple convolution between system response and the half-duty wave, and that's how we calculate our DDK.
So if you made your repetition cycle half as big or twice as big, and then you did that same deconvolution, do you get the same answer out, or is there some difference?
Yeah, it's a matter of statistics. For instance, the decays that I show you, we measure like 20 periods, okay? And then we stack 17 of those periods in order to get that decay. And the errors that I present to you related with that decay were statistical errors that we get from every stack on the data.
Good.
Okay, thanks.
Thanks. Who'd like to come up next? Looks like Daniel's gone because there were three people that were going to present.
Just 1 second.
Yeah, no problem.
La función de transferencia es para calcular el telúrico que, digamos, es tu señal para que tuviste, para que recibe tiene una señal que contiene el señal que está en digamos, la señal que tiene y la señal que natural, entonces, si tú calculas tu respuesta a partir de esa señal curiosa, tú tendrías un entrenamiento muy mal. Como la cosa significa normalmente entonces tú tienes tu concentración inicialmente, es la concentración magnética de la pelota y tú vas a hacer un uso con el campo HI que mide en dirección remota. Y eso hace una convolución del sistema y tienes un campo de sabor y ese campo de va a ser variablemente y va a ser distinto para cada sabor.
This one.
Mira, lo que pasó,
And then here's a laser pointing computers, and then this will change your slides if you want, or you can use the computer. Totally up to you.
Los procedimientos en ese lugar son muy densos, entonces cuando ocurre una inversión adjunta, o sea, tanto los datos de ese y tratando de meter con eso, la solución de ese conductor queda muy densa.
Hi.
It's a great name for a company.
That name says like a little about ourselves. So my name is Eduardo Arcon. I'm working in AWAX. I'm a geological engineer. We have a lot of geophysical engineer and physical background, and I'm working in the geological side of the company. But I want to introduce you to a little work that we are doing. At this moment is more an observation study because it's undergoing right now. So I can't show you the whole picture, but I can give you some insights about what we are doing. We are a company focused principally in groundwater issues, groundwater problems through the physical surveys. We have a little project about aquifer research, a study that a company is doing, and we are performing some geophysical survey. The details of the aquifer is that they have like infiltration pools, and they are trying to inject 50 to 60 liters per second into through these infiltration pools to an aquifer. I don't have the details of the aquifer, but I have the information about the Vado zone of the first 30 meters, 40 meters that we're focusing our work. Really, the research is more than 50 days, but our work was a little short, 15 days, with an on and off infiltration. They start pumping some water, then after 2 or 3 hours they stop it. Then it was a moving system, and the geological frame, alluvial sediments, first 30, 40 meters in the Vado zone. So we tried to understand the problem and try to find a good solution to do a visual and numerical model about infiltration and about trying to know what's happened in this process. So we choose some electrical resistivity tomography in 2D versus time. One 2D line per hour through the 7 days, and one every 24 hours for 15 days with a gradient array. The main challenge of this survey is that we needed a fast acquisition because we had to take one snapshot of the subsurface every 1 hour, but also having high quality data. So we designed our protocol especially for this survey. We did some, like a control acquisition with a big line of electron resistivity tomography, ERT. What can I tell you that is that we have 2 infiltration pools in here that are really big and some small ones. And we did this to have some knowledge about the subsurface because we didn't have any geological information from our contractor. So we took this information, we really did for other profiles that are in these images, just trying to know about the subsurface of this area. And we did a little simple model with 4 layers. The most superficial width over 800 meters, and a second one between 200 and 500 meters. The third one is this one right here. Also over 900 meters. And then per layer, we have like 35 meters with these 3 layers. And the last one with a little more than 90 and also 150 meters, the 4th layer. So we thought, well, we have 2 layers that maybe are alluvial fans, big with a big granulometry, great high conductivity, hydraulic conductivity, and then we had 1 layer between that. This one between 200 and 500 meters. That is going to be interesting for us. So we did that survey. We took this profile, 7 days, 1 ERT profile per hour, and through those 15 days, 1 ERT profile per day. We did a data inversion constrained with a time-lapse inversion, and we generated this video animation. It's really raw because it's a data that is not produced to be in a presentation. So I'm going to show you.
So where are you injecting the water?
Right. That's important. They started to inject in these 4 little pools the 5th and 6th hour. 5 and 6 hours in our we have like 0 to 150 shots, and they started to inject in shot number 5 or 6, and then here it was a little bit later. This kept infiltrating through the whole study, and this it was an on and off situation. So you're going to see some change in this area and some change in this area with the resistivity data that we got. So this is, you can see that it's going to have some change in this area, and then like in 9, 10, 11, it starts to inject over that area. You can see this is our color chart with resistivity, low resistivity, and high resistivity. And you can see how it behaves in this area and this area, and this layer starts to reduce its resistivity, and also this one. So we can see.
So you've got this really low resistivity blue area that's piling up there. What's happening here? So you're injecting at the top, is that right? And then is that a region that's cut off from in the inversion, or?
At first we thought that this one was maybe an artifact induced by the type of inversion, the time-lapse inversion that we did. But after do some heavy review of the inversion, started to see that this started to appear as soon we started to do some infiltration. So at this moment, we don't have a main hypothesis or main interpretation. So we're having like different ideas of what could be happening. For this moment, it's only an observation point. So to try to understand a little bit about this, maybe some infiltration paths that we could find in this area. We just did a little data mining of the resistivity data that we have. So
time-lapse tends to preserve the strong features in the model from the initial time. Did a control separate time-independent test of the models?
Yeah.
You inverted them and they should do the same.
Yeah, exactly. Yeah, we did also. With this acquisition, we acquire profiles every 24 hours with more resolution. And we also did inversion with every data that we had independently. So we just tried to do a lot of comparison between the time lapse, the individual profiles, the main profiles, and the daily data that we acquire. So we thought, well, let's see the numerical side of this. So we took each of this line represents 1 pixel of point in this resistivity data, and this is true time every hour. And we put some color when resistivity starts to get smaller, and red when it's the same resistivity or it's little change. So we started to see some blue spots or more blue. This is the area where is the main pool, and this is the area with those little pools that they are constantly in an infiltration mode. And then we did some graphs. In the main pool, we can see that the resistivity we started to measure in a control nearly 500 meters, and when the infiltration period started, it just dropped significantly the resistivity over 100 meters and stayed in that area until the infiltration stops. And then we had like little curve until the moment that it started again an infiltration period. So we have like a sequence of humectation through the infiltration, and then it stopped and started the dewatering of the zone. So we saw this the big pool and the small pool, but the small pool just kept receiving water from infiltration. So we had like a good steady moment of change from resistivity 200 meters on to 90 and 80 meters. And a little more deep, 7 meters deep, with one of the little pools. We also had similar behavior of this resistivity. So our next step is trying to do some numerical modeling with this information. We're thinking about multi-physics approach and a synthetic mode that we can use our resistivity data that we're having and do like an optimization and trying to find some hydraulic conductivity through this sequence that we're getting. And I guess that's all I could say, because the next steps are going to be really long, but we're trying to use this information to get the great model, a numerical model, and maybe perhaps a visual model about the behavior and on the Vado zone. Sorry for my English, it's not very well, but
Great.
Are there any questions?
I'm sorry, I don't have a geophysical background, so I cannot give some answers about the inversion or because it's difficult. I don't know all the details, but I know the geological side, so maybe that could help.
Quick question: did you acquire IP data as well, or just
No, because we had to take very fast data, and we had to do some balance between time and quality and information.
Any other questions? Oh, thank you.
I'd like to mention that's the traditional IP system that you have to move and we don't have time. But our system, it's distributed acquisition system that you can measure at the same time all places. All stations. All stations.
Thank
That
you.
can be useful.
Perfect. Daniel, would you like to?
Yeah, sure.
Thank you. So if you like, this will change slides.
So yesterday I asked some students to present something. They didn't want to. So I'm here. No, but they, some of them, Ariel actually, and Renzo, sent me some of their data and their results. So I'm going to show you some of their work and I will try to focus on some problems that we have had during the process. So I will show you some examples of EN methods applied to volcanoes and geothermal systems in North Chile. So one example of one volcano and one example of a geothermal system in North Chile. During the last years, actually, during the last 5 years, we have been measuring in several places in the Central Andes and also in the Southern Andes. As I was talking with Doug and Vinci yesterday, there's a place called Laguna del Maule, which is here, more or less, where we have a lot of measurements also, and there's also a geothermal system there, but I'm focusing in this area today. And here, in this place, in this red dot here, there is El Tatio geothermal field, which is very well known in Chile, also maybe in South America, because it's one of the largest geothermal system with an extrusive system with geysers and multiples and other kind of stuff. And it was very studied by people from the Enel and ENAP and other companies during the 90s and during the 80s. So there's a lot of geophysical data there, but it's sadly not available for research or any other use. So we decided to go there and measure again and try to gather our own data and make and publish a model, a geophysical model of that area. And also in this place close to El Tatio, which is here, there is a chain, a volcanic chain called San Pedro Linsor, which is there. I will make a zoom in a couple of minutes. And that's where Renzo Mancini is working, and I'm going to start with that part. So this is a volcanic chain, as I told you. It is a very nice place. This is just a picture from Google Earth. These are magnetotelluric stations, broadband stations. Each of them, there are 20 around San Pedro volcano, which is here, and Linsor volcano, which is somewhere here. So this is the chain. As you can see here, it has this very large stuff here, which is a dacitic dome, which is one of the newest extrusions of this place. The lavas extruded here are quite different than others in this area. but it's not the only one. Here you can see another one, and to the south another one too. And this is one of the newest expressions, as I said. San Pedro is also an active volcano with a fumarole and some eruptions during the last years. So each of these stations was measuring in the field for 24 hours or so, and most of them were measured during 2016 and 2017. So one problem, talking about problems, is that we have not a very good coverage of the area. That's because we have a very strong lack of instruments here. So we have only 2 broadband stations, and that's always a problem because we have to work in different places, work in difficult places, and in this case, for example, the lowest station that we have, maybe this one, is at 3,500 meters above sea level, so it's quite high. And these others at this side are like 5,000 meters. So
What's the horizontal scale on that map?
Oh, I don't have it here. But these stations are separated like 1-2 kilometers, right? No, 5 kilometers.
Okay.
So
Yeah.
this should be like 5 kilometers.
Okay.
So that's the.
Are there roads, or how do you get around?
Yes, there are some roads from this side. You can enter this area, and then round the volcano chain here. There's another way. You can see a road here. Maybe it's possible to see and reach this area. Yeah, there are some roads, but after some drive, you have to walk in some places. So and also an interesting feature is that here at this graben, which is here, maybe you can see that now. Here, there is the very new geothermal plant which is operating in Chile since April. So at this place is the first geothermal plant. It's Cerro Pabellón. So this is an area which has a very strong geothermal interest, and that's why we decided to go there and to try to study these volcanoes. Here's another density. So one problem was the topography, as I said, and Renzo was struggling a lot of time, maybe months, I don't know, about the discretization of the area because, as I said, you have a very strong difference in altitude between this side and this side of the volcanic chain. Here you are at 3,500 meters, and here you are between 4,500 and 5,000 meters. So it's like 1,000 meters, like a step, no? 1,000 meters in altitude. So it was difficult to discretize the area. And just to show that, Renzo sent me yesterday some plots of their first data fit of a 3D inversion. This is the data. This is, as said here, ZXY and ZYX, red and blue, upper resistivities and phases. This is period. And the continuous lines are the predicted data. So you can see that the misfit is, the data fit is really bad. It was really, we were really traveling with Renzo at the beginning, and he tried to struggle with this problem quite a long time. And after some work, he got this. So this, yeah, you can applaud.
20 laptops and data points, did he?
Sorry?
Did he leave out some data points?
Yeah. He raised quite a lot of data points, it's true. But
It's easier to better.
it's easier this way. It's true. We were more troubled about the first part, no? As you can see here, at these periods, at these high frequencies, the data fit was really, really bad, also in the phase, and after some playing with the grid, with the reading, with the size, cell size, and this kind of stuff, we could reach a much better data fit.
So is it mostly a problem of cell size?
Yes, and also because at the beginning, just to try, we consider no topography, and we got this kind of results. So with very roughly discretized topography, we got a bit better results, but afterwards we needed to change very carefully the cell size of many of them, just to get better results in the data feed for the first periods, for the shorter periods. And I wanted to emphasize this problem that we had in this case, because I have been working in the Andes since some years ago, and I hadn't seen this kind of misfit before this case.
What is the error scale of your data?
Sorry?
The error scale of your data?
It's not put it here. No. But well, for this part of the data, it should be smaller than the points. For this part, it should be larger. I mean, but maybe we consider always in the inversions an error floor of 10%, more or less. Well, Renzo knows better. So also, this was also done by Renzo. We in every station that we measured horizontal electric fields, horizontal magnetic fields, plus vertical magnetic field. So we also work with the tipper, and as you can see here, here's a plot. Well, I forgot to change this to English, but this is a plot that shows how the data feed for the tipper, this is TZX and TZY, is much better if you consider a much larger grid, which is fine. No? So you are considering a very large grid. Here is like 55 kilometers larger in X and Y directions. The grid is much larger in the horizontal than in this case. And this is the similar close stations, and you can see that the data feed with a much smaller grid in the horizontal is also very bad fitted, and in the case of a larger grid, it's also better. So,
do you know what boundary conditions are applied in those cases?
In these two cases, I'm not sure. No, I should ask Renzo. Renzo, you know, which boundary conditions were?
Para la ingeniería.
¿Para la inversión? Sí.
Sí, es que no entiendo bien la pregunta, en relación a, o sea, en relación a qué las condiciones de borde, aquí.
O sea, las condiciones de borde de la inversión. These are boundary conditions for the inversion, ¿no?
Yeah.
Yeah.
Ya, el piso de error, 5%, o sea, de 2%, y se consideraron todos los componentes de una ZX.
So he says that for this case he considered the whole data set, not tipper, no, sí, también, sí, tipper too, and an error floor of 5% in some cases, and well, if you see the area here, this is I mean, what Renzo did was just set this area at the middle of the grid and leave a lot of space to each side just to get rid of some problems at the edge of the grid. So,
yeah, but in one case you said 13 kilometers, in the other case it was 155.
Yes, from the central part of the central part of the grid is like this part, and just in the first case was just a bit larger, and the second one was much larger in the horizontal.
So that's kind of why I was asking about the boundary condition, because if you've got maybe just a really simple boundary condition and you're really close in, that might cause some problems. But if you put a simple boundary condition, it's a long way away, things can adjust.
That's the way we deal with the problem, because we leave this inversion process to make some boundary effects at the very far boundary, actually.
Do you know what boundary conditions are applied? In
this case, no.
Is this mod-EM?
Yes, mod-EM, yeah.
And they're applied automatically, or do you have some?
We have some control about some parameters.
Yeah,
we have some control about some parameters. Yeah. But I don't know which one we're using in this particular case. So that's with tipper, and this is the result of the model. This is an image. It shows two cats in the 3D model. The cuts are shown here. This is A and A prima here. This slice is the north-south, and this B prima and B is here. So it's a complicated way that Renzo likes to show slides. And why we cut here this model is because here there is an older, very old hot water springs in this area at the southwest of the volcano, and we can see a wider conductive structure close to the surface in that area. The volcano is more or less at the cross of these two slides, and also a larger, which is here, and also a quite larger conductor in this area, which is in this part. So we were looking for, this is one of the slides which resumes a bit his work, but we were trying to look for magmatic structures that deeper, a bit deeper than this. And we fortunately could have access to some older data from German groups who were working in this area with magnetotellurics too. So Renzo included this in a newer version just to image these conductive structures, which are a bit deeper in some cases. So that's about this volcanic chain. And just to show another example, is the work of Ariel, which is there. Everybody knows him now. And this is a work that has been done in El Tatio, La Torta geothermal system, which is very close to the other place that I showed you. This is a picture of this site. It's full of geysers, as you can see. It's a very nice area. If you have time for the next time, you should go. It's nice. And this is a place which actually is in this moment is since several years is used mainly in a touristic way. I mean, it was there were some projects to extract some geothermal energy in this area during the 90s. Therefore, it has been measured heavily during the last decades. But as I said, there's very few data available for research. So we decided to go there and measure again. So the same problem as before. This is El Tatio. Is here. The volcanic chain that I showed you before is more to the north here. And this is another dacitic dome, which is, according to the studies that have been done in the area, this is at the top of the heat source of this system. So the heat source of this system, which has an outflow in this area, is more or less here to the southeast. That's why we measure a couple of stations here, but the accessibility in this area and to this place it's really difficult. This is really high altitude terrain, a lot of topography. It was not possible to go by vehicle, by four-wheel drive vehicle. Also was very difficult to walk in these altitudes, also 4,000 meters or more. So we had to measure only in this area, close to El Tatio and a couple of points here. We were hoping, and we are hoping, to get some more data from the previously measured campaigns for geothermal exploration during the 90s, and get some of this data from these companies. And we are trying to do some communication with them to access to this data, because they have covered all this area with NT soundings and another kind of soundings. TDEM, for example, also has been done here. But the accessibility to this data is difficult, and we are trying to fill this enormous gap here with some of this data, if possible. Clear if we're going to be.
Can you tell me a little bit more about this acidic dome?
This one?
Yeah. What is that?
Oh, dacitic domes. It's made of dacite, which is a kind of lava which has a strong signature of silica. So these are domes which were formed with a very viscous lava, which erupts, and as you can see here, for example, in this example, the lava should have go out of the surface, more or less in the middle, and it travels just a short distance because it's very viscous. So, and that's a difference with some other volcanic edifices in the area. So, and this is more or less new. I mean, it's like 20,000 years old. This kind of structures, as in the other case. So,
and how did you spell it? Is it LAC?
dacitic, you mean?
Is it, yeah?
DHC?
Oh, D, oh, day, like in Dayside.
Yeah.
Yes, I see.
Yes.
Okay, sorry.
So they were also present in the other area that I showed.
Yeah.
So this is it's more in a more in a previous stage than Renzo's work, because Ariel is still working in inversions, and maybe we will be able to go to this area again and measure a bit more, or maybe we will get this data from these companies to complete the data set and to cover much better the area. Until now, this is a very preliminary result. We are also working with this ModEM software to do 3D inversions with this data, which are more or less controlled in this part, but of course in this area it's very bad controlled in this place. So this is a cut which goes from north west to southeast. No? Okay. So El Patio is here, more or less. This geothermal, I mean the outflow of the system. This is T18, which is here, and the dacitic dome is more or less here in this figure. So we have to, we are actually trying to measure another methods in this area, particularly here in this part where the geysers and other outflow systems are. And we're trying to also to complement this data set with TDEM measurements. We started with this with a few profiles during last month, October, and we're going to complete these measurements during March probably. And we'll try to model this and try to model this data together, hopefully. TDEM plus and T in this part of the area at least. So, well, that's data fit, but that's just for the preliminary results. It's just to show you something. But that's what we have until now. So that's the presentation. If you have any question, please let me know.
Thanks, Dan. Are there any questions? No? Is there anybody else who would like?
Thanks for your presentation. And from your perspective, what is the better results that we are having in this area in the geophysics department?
Well, if you see in this part, now this is like a these are only two cuts of this 3D model which we have here. We were really looking for magmatic structures in this area, and we are trying to identify them and trying to have an idea of which resistivities should have, for example, different kind of lavas. So we are trying to work in that direction now. We're trying to interpret these models, also well, the complete model, not only these two slices, in this way. The idea of this work is also to complement these measurements with measurements will be carried out in Cerro Pabellón, also just to control how the geothermal system is changing with the work of this geothermal plant there. So it's like a complement. If we understand better where are the heat sources for this system and others which are in the area, identifying magmatic structures, we will be able to understand much better how this will evolve, for example, how this system and others will work and evolve when you exploit them. That's the idea.
And this, I was just to say, so do you think like there's just one really big magmatic source underneath that's feeding all of these, or there's a whole bunch of individual sources?
No, I don't think so, because it's these kind of lavas are quite different than the ones erupted in some other places like this. So there should be some differentiation in the crust, and also in this part of the Andes is quite affected by a body which is known as the Altiplano Puna magmatic body, which is a very large feature, which should be in this image right here. So that's a very large magmatic system body, which is in all the Altiplano de Puna of the Andes, and related to these small volcanoes, which are not small, but it's small compared to others, and these small eruptions should be related to, I think, small accumulations of lavas of magmas of different kind in the crust. I think so. So one should expect to find, as we found in, for example, in Laguna del Maule, different resistivities, which, for example, the acidic magma should have, for example, between 150 ohmmeters in resistivity, which is very different than, for example, much more basaltic magma, which should have like between 5 and 10 ohmmeters. So one can see with resistivity images changes in the composition of the magmas and the pressure and temperature, of course, and all that stuff.
Is there anybody else who had? Anybody else who would like to present or has an image or something that you would like to chat about?
It has to be in my computer.
Okay, sure.
Well, hello, everybody. I'd like to show two really little things, because as with the spirit of show some problems, I've been working or trying to work in hydrogeophysics as a hobby, maybe, and environmental problems. So I have identified the need for, maybe you talk about this in the morning, I couldn't be here, but the need of a relate electromagnetic response of the ground with hydrological properties. So there's a research you can do about recollect a bunch of people who have been trying to do this in the past. So in the way of relate some geoelectrical study and a model, or a geoelectrical model as a whole, to properties of the hydraulic conductivity of the ground. Hydraulic conductivity relates the viscosity of the fluid, relates the and some other things that the viscosity of the fluid and some other property, I don't remember which, of the ground actually, maybe related to granulometry or something like this. And it controls the way that fluids flow through media, through porosity media. So you can use actually the IP response to generate this correlation between electrical properties to some specific estimations of hydraulic properties. So you can use that to try to validate this. So what's the problem here is that, as far as I know, this is not common in Chile. I don't know if it has been made actually. So the problem I'd like to present is the we need some brave contractors to or some brave students to try to do this. So yeah, so that's one thing. If you excuse me, I will take questions after I show you the second thing, which is the following. Okay. And this is a work of some totally different area. This is exploration, mine exploration. So this is interesting for me at least because this was made in the field. I was actually in the field during the processing of that data, and this is very interesting because this was a really small mine, which was being mined at the time. So there's been some huge socavón. How do you say socavón in English? Anybody give me a hand? A big hole in the ground, so people get there and mine. This is a property that has been mined for centuries. Actually, there's more than one grave around because of people dying in the mining process. But anyway, it's hundreds of years. So this is this big socavón. And as I was in the field acquiring data with some help, there were an army of geologists mapping there. So when I got this first preliminary model, I show it to them. So they tell me, no, that's not what we're seeing there. We have holes, we have our equipment, we have our, let me say, lupas there, and we don't see that there. So we start to work in that, and actually, then we get here at the final situation after 4 days of working together, and they were really happy because they actually were seeing this there. Some parts of it, maybe, so they can believe with better faith of what I was showing them. Same thing with resistivity. So the problem here is, how do you discriminate when you're done about your model? Because I could take from this, I could be going anywhere, but the data of the geological part of the team were very strong in directing that train to something better from their point of view.
Is this the same data set that's being inverted?
Yes. No. This is raw, and then after process and cleaning data and selecting because of quite errors. High errors were out, in high errors in almost every way. And then there's also a shift factor there that ask for the model to be more with high gas rugosity and other things, mostly about cleaning data. And also the use of reference models from the geological point of view. So the thing here is that after doing that with this line in particular, I get to well, all the other measurements the other lines that we measured were controlled by this. So I don't know if I can zoom this with no mouse, but if you could see, there's a good correlation between the directions of the survey. So actually, this project was after drilled, and they were really happy because they found what we showed them. But the important part is that for this longitudinal line, we made the stronger common process, and and then we use it as a base for the rest of the inversions, controlled inversions, and get to it. I mean, we did a good representation of the GLE, and it was making people happy. But how do you discriminate? And that's the question from me, at least. So that's it.
So do you use the misfit maps at all as a diagnostic as you're doing this?
Yes, I did. I did, of course. All those models that I showed you, they were asking for different things to get to convergence, but they all converge. Some model to the asked misfit. But actually, playing with the chief factor for this line is a tricky way, after all, of get your model to converge. Yes.
Sorry, I got a bit lost in the middle. You were talking about how the resistivity of porous media,
yes,
is mainly controlled by the amount of fluid content. And then you showed us the result of a mine site with a sinkhole. That was the word they were looking at. Sinkhole.
Sinkhole? Ah, sinkhole. Sinkhole.
Right? But in a mine site, you will probably don't have a porous medium.
No, not at all.
You have a fractured medium.
If so, that was two different problems.
Yeah. But so far, the main physical models for modeling conductivity of resistivity are designed to work with porous media, being it RT, Waxman Smith, or Brunei Hageman. They are all designed for porous media. So the conductor that you're looking at in the results, what does it stand for?
That's searchability.
You mentioned that the geological mapping.
That's searchability. I'm sorry.
Was aiming at something similar, but what it is was a layer or an ore body.
No, this is resistivity, and colors are inverted. These reds and Kelly colors are not conductors, isolators. So in this case, this isolator is mapped with a rock and gabbro, no, granodiorite.
Granodiorite.
Okay, so this was a granodiorite, and on top of that there were some lavas that were actually fractured. And this year in the north there was a lot of rain, so they were a little more conductor than you would expect because of all the inlet fractures. They were hydrated.
So that's for the rock, and the less resistive parts are the overburden.
Overburden? I don't know.
Cobertura.
Cobertura. Yes. Sedimentary and volcanic overburden in this part, and granodioritic basement in that part, as roughly, and a lot of structures there that could be seen through some characteristics of the sections. Actually, they were found at drilling, the important ones at least. That's it. That's it. Either way, this is resistivity, and the first one was, well, here it is. This is well-colored resistivity, and this is chargeability. So that's it. That's it. And in the first time, I was talking about something totally different, related to high dielectric conductivity. That's all. Okay.
So we should all keep calm. Your t-shirt.
Make sure.
So well, yes, you should. We all should.
So is it, like, come on up.
It's a really bad presentation, but it's the best. No, it's we crashed. I did it in 5 minutes.
No problem.
In the lunch.
No problem.
Yeah. Why? Well, I had a really small presentation in 3 diapositives with 2 slides with any results, because I don't finish the program to show the results now. But the
This one?
yeah. I think no. No, there's another one.
This one.
Yeah. Okay. Oops. Yeah, it's a little. I'm a little bit nervous. I try to show what I want to do in my thesis, the idea and the problem. That is.
If you'd like, this is a laser and this will change your slides.
Okay. It's in Spanish, but it's hydromagnetic inversion of the hydromagnetic data for generate 3D models of magnetization in underground, and that's the idea. The professor had a paper very similar, but which tried to find susceptibility models, and we is not the goal of this thesis. Well, in fact, okay. Well, another magnetic survey is a technique very used that when we have a plane flying around the surface, trying to be close to the surface, but it's a little bit difficult. And well, we have these maps obtained from these flights. We have a lot of data in the north of Chile. We can see a lot of anomalies in this map, and we have all this anomaly, and we try to think what happened this anomaly. Well, we will use this area, and we saw it here, and we try to use the magnetic anomaly and invert it to find in a 3D model of the subsurface, a model of the vector magnetization in this area. Well, we have a little problem with this because the hydromagnetic survey take a measurement of the magnetic vector, but we don't know what is the direction of this vector, because it's measurement in the preferred direction of the vector. Well, it's changing every time and every day and every hour, and depend on the time in a lot of things instead. Well, but we can calculate the anomaly, but we don't have the direction. So if you wanna find a vector, we have to take the three components of the vector in magnetization, having the x component or y and zeta, or I don't know, in another kind of system, visual system. Well, we have the approximation here. We have to use the G, which is the Earth's magnetic field calculated by the ERGF model, and we need the time, but in some measurement we don't have the time. Well, what I did a little bit, a lot of equation, but we have just 5 minutes to do it. But I using for this model of base cuerpos, bodies, this to construct the space that we will invert. We have the solution. We have a linear problem here that is a lot of equation, but we have the magnetization for any kind of square. Not square. It's a figure that have this configuration with any size in theta, x, and y, and any magnetization. We have this paper that find an analytic solution from the magnetic field generated for any figure like that, and with the magnetization in y, in the component y right here, but I expand the solution to the other components and I have now a general solution. So I use this like my base function to the inversion. Well, that's all the visual things that I have, but I finished the G matrix now. I have all the green functions from any space. I finished the space, the parameters, all the space and all the matrix, all the green functions. I have the D, and I make a test now using just this really normal and known equation, the least square method, and well, this not it's really bad results, but I want to try to use now another method with regularization and with regularization that solve the problem that is trying to solve. What is the trade-off existing in the depth of the source of the magnetic anomaly and the size of the size of the magnetic anomaly. How can you discriminate if you have a very magnetized body in a really depth, or we have a really shallow body with a slow anomaly? I try to find that, and I will use some regularization models and regularization equations in them. And before that, after that, I want to try to use Bayesian method to invert that and obtain a result. Even if you don't have enough observation for use that method or something like that, and that's all. I don't have more slides. If somebody have a question. Yeah, no, yeah, no.
Thanks for the presentation. I found interest about the development in the expanded solution and to use a Bayesian method.
Yeah.
Can you explain us more about it?
It's really okay, but in a few words, it's method that do not use equations to try to, you use equations to try to find the solution, but normally you don't have I can't explain. You use probabilistic method. You try to find the more probabilistic solution, or if you try to, when you try to,
Make a guess.
Yeah, you try to make a guess of the results using your information that you have before the inversion. For example, if you know that the solution have to be like something, I don't know, like a parameter you know, or you know that the solution can be bigger than a number, you can use this information to try to constrain the models that could be possible to explain the data, for example. And it's a lot of methods, and Nati and Nico try to use it all the day to find some solution. And I don't know, it's a verbal recognition, but in English it's a little bit more difficult.
¿Cuánto tiempo estima más que te va a tomar la inversión bayesiana?
Es una muy buena pregunta, pero depende más que nada de la cantidad de celdas que vaya a ocupar.
¿Pero tienen algún cluster aquí como para hacerlo más?
Sí. We can use Leftraro. It's a cluster in the CMM. No. The name of the cluster, Leftraro. So, okay. When I try to invert with less queries, take 2 hours, and generating the G matrix takes 3, but probably take a lot of time. Okay. Thanks. Bye.
So I think what we'll do is we'll break for coffee. That's all set up, and then we'll come back. I'll give you a bit of a tour of GeoSci, some of the resources that we have there, SimPeg, and then the 2 styles of apps that we have. So the like slide bar ones, and then how to actually do computations with SimPeg. So.
No lo he quemado. Tengo que usar el método.
¿No escuchó siempre sobre una técnica que se llama resonancia magnética nuclear?
Sí, la iba a presentar.
Sí, porque en su momento yo trabajé con que ellos van a poner un resonador magnético. Y eso no era para buscar. Después hice un curso que hicieron, pero con la herramienta de pozo, lo utilizan para el petróleo. Y hay un parámetro que ellos asocian con la permeabilidad, que es la difusión. Entonces, porque ¿qué es lo que pasa? Que cuando tú trabajas con, tú puedes conseguir la resistividad, tú puedes ver que el medio es poroso y si lo puedes asociar con la resistividad del líquido. Pero aquí viene el otro detalle, ¿cómo tú sabes si se mueve o no se mueve? Ya es otra cuestión de que no, con una sola medición no lo podrías hacer. ¿Sí? Y si tú tienes un sistema que, como tal, geométricamente no cambia, solamente se mueve el fluido, tampoco va a haber mucha variación en la resistividad. Pero eso, búscate por ahí a ver qué te puede ayudar la RMN, a ver, para asociar algo con justamente la capacidad que tiene un cuerpo de polarizarse. Dice que no es muy móvil su fluido. Entonces, por eso es que yo uso a esta discriminación el método de libre resistividad se practicaba. Ahora, la herramienta de SMR es espectacular. Pero tú sabes que es muy buena porque tiene una gracia que ahí, bueno, aparte de este parámetro que tú mencionaste, que es te encuentro tan chévere que lo que esa cuestión hace es que interactúa directamente con la partícula de agua. Sí. Entonces, como que la hace resonar en su funcional, como se puede. Porque es una cuestión que tiene una firma que tiene cada elemento que es la constante giroscópica, la frecuencia del amor, que es la que tú utilizas, que es la misma frecuencia con la que tú inyectas el cambio exacto. Pero la cuestión... Y tiene la limitante de la profundidad. Sí, pero es que los resonadores, aparte que son caros, el más famoso es el Loomis, que es el de ahí, de los franceses. Y es muy tedioso trabajarlo, pero nosotros teníamos para hacer hacer un perfil, tenemos que irnos en 3 camionetas porque son como 24 cada de tamaño. Y la gira de 100%, la pase de 150 metros, pero también tiene pero sería bueno en los desiertos de Chile, sería muy bueno porque no hay ruido. Nosotros lo utilizamos y teníamos un pueblo como a 200 metros y eso nos dañó todas las animaciones. Pero ese parámetro, yo creo que no sé si se puede usar como difusión o difusividad. Entonces, eso es para saber porque...
Tengo la siguiente consulta. Estoy conversando con Eduardo y me dice que él está
porosidad.
Entonces, en este caso, ¿ese parámetro conversión con isometría o con magia?
Para saber si se mueve o no se mueve. La difusión.
Pero no se sale
No sé, por eso que a ver si eso nunca te sabes si funciona.
¿Cuál es la duda? Sí, la duda es la siguiente, que si inicialmente íbamos Eduardo y yo, y Eduardo ya no puede ir, entonces iría yo o conversar con su marido para que esté presente, además de mí. Sí que... Ya, bueno, que las cosas son en este caso cuando se ven, pero se me queda la cumplidor y él también me maneja. No le puse lo último, que se ve un poco recortado. Sí. No, ahora sí lo oigo. Sí, pero mi duda era esa, si iba sola, de qué lugar no iba, o conversaba con José María para que estuviese presente por ese tema. Sí, disculpe que no le entiendo. Ok, y la otra consulta es que con nosotros para fijar el día. Ok, sería el día. Ya, lo decía por si acaso era necesario que yo llamara a Felipe o esperaba simplemente su respuesta. Ok, perfecto. Está bien. ¿Consiguió la forma? No, que se había conseguido las hojas que estaba buscando.
No es autodidacta, sí.
Ah, ya. Bien. Bueno, era eso, Isabel. Muchas gracias. No, falta todavía una hora y media.
Interpretación de datos cívicos.
Bueno, sí, estamos conversando. En este caso, están trabajando algunos compañeros. Sí, ya lo presentó. Bien, no dijeron nada. Sí, sí, lo hicieron bien.
No sabía si de información involucrada, pero hay poca experiencia de este tipo de datos. Un poco más de que como balancear la relación pero el problema es cómo lo modelan, cómo lo entienden cuando recién
No, ya está.
no lo sé, si yo grande, no lo entiendo.
Bueno, en eso por ahora.
Pero
Eso de China,
Realmente, y nosotros realmente el trabajo es para probar algo distinto con un cliente que tuvo bajo el poco dinero que tenía, poco conocimiento que no sé, qué buena posibilidad. Claro,
Venezolano. Buena, yo pensé que venezolano. ¿De dónde son?
¿En serio? De Caracas.
¿De Caracas los dos?
No, yo soy de Los Andes, de Trujillo. Pero tú viniste de Chile para acá.
Sí, nací allá, 2 meses, mi papá se vino a la
¿No quieres que te quedas con tu
Yo de Caracas. Felicitaciones por la versión. Hermano, así lo puedo, así lo puedo.
Yo
sí, así vaya avanzando. Estoy haciendo de titulación por geología y un poquitito. Son departamentos separados, sí. Trabajando, pues lo veo como tú, que estás ahí en la toalla, yo también. De poco se va, pierdo esa
Gracias, yo estoy comenzando con el proceso de hacer la simología como un estudio usando modelos estadísticos parecidos a lo que enseñó David al final. Es un modelo sí, claro, algo en ese sentido. Primero estoy recogiendo como haciendo la parte bibliográfica de estudiar parte de los modelos anteriores. Esa es parte de a futuro hacer un modelo
para una persona, ¿no? La persona que se pone la culpa y yo entonces soy la única persona que tiene familia. Entonces le hago propuestas. Para hacer la ejercicio, es algo similar con lo que está probando la persona de abajo. Pensando acelera que hay un medio que es conductivo y vamos a utilizar la atención. Lo que dice atención, tú no vas a hacer una especie de usando la atención de la
sacando el derecho de los malos.
Pero pues hay que utilizar siempre hay que utilizar las energías superficiales. Porque a veces el pozo hay que llevar el ritmo de la otra es, si no hay pozo, lo física más joven. Imagínate de manera más rápida las dos cosas.
No tienes que dar una
¿Tú sabes qué es lo más complejo? No sabes qué es lo difícil de vender que no sabes lo que es ahora sí claramente tiene muchas limitaciones, ¿no? O sea, al final cuando tú ves que no salió o no se dio lo que tú querías, se nos abre y queda la dice, entonces eso es complejo. Pero hacerlo como claro, que el momento de eso, o el transporte, si me comes tu terreno,
Cuando
cosa que no tenga miedo de que si no funcione. Pero si hay una ayuda, ese camino no hice.
La página.
Porque a lo mejor me tengo una compañía, y yo para acá, mira, necesito que me haga un modelo físico de esta cosa. Se viene y hace, y mejor y uno de la misma escuela y hizo lo mismo que el mismo sitio.
Y eso explica una vez el método del conocimiento muy lento.
Que nos sorprende que todos de apoyarte y aquí
Entonces es como jefe, cuando dice, vamos, muéstrale lo que quieres hacer. Ojo, muéstrale que cuando diga cómo se explica, no diga cómo se explica, es así, es como que muestra lo que quieres, pero no le puedes explicar lo que tú quieres hacer, porque tienen el miedo de que vengan y digan, mira, yo digo lo físico de, mira, necesito que me hagas esto que me hagas, porque eso es lo que llaman el bypasseo. Tienes que ver que no te bypasseo, es lo que te dicen inmediatamente no. Entonces eso es una nada, como porque tú no puedes mostrarle. Entonces, ¿cómo hay una imposibilidad?
Nosotros para nombrar una cosa oscura de manera separada y vemos todo.
Más se hace, más una posibilidad que estoy sorprendido que siempre se va a comer tú tienes un sobre todo
reducir costos y sondar una cadena de sondado. Porque tú puedes hacer una que van a caer a sondar todo el tiempo, va a ser 5 o 10 sondajes que se iban de entrada. Lo físico, y después, ¿qué cosa? Más sondajes para validar el modelo. Si no eres físico es realista, se acerca a lo que a los sondajes como tal, ahí sí ya va a hacer sondajes, pero más enfocado al área que te va a entender el modelo. Así que pero así va a ser
y Natalia que hace mucho son
luego hacen una cita, hacen una cívica todo. Después de los 2 meses de sector perfecto, ciertas áreas donde tú consideras que puedan haber hidrocarburos, hacen una doblez. Entonces, la doblez está regulada. Pero algo de las 3 yo le tardas 12 minutos. O sea, a los 3 años que tú ya comienzas a tener, bueno, aparte de ciertas cosas que pasan por afuera, como los 4 o 5 años que comienzas a hacer la perforación para los $100,000 al día.
Entonces, nadie se arriesga a hacer algo. Pero como acá también es una barata, no sé si quieres, pero no pasa eso. Igual sale mucho.
La sísmica para navegar con la perforación. Por ejemplo, estaban guiando, entonces la florena y tirando acá, y entonces cuando sales a atravesar la cita, y la calculas el tiempo que tardas en sacar. Cuando tú cambias de nivel, tienes que cambiar la boca. Tienes que sacar todo eso. Estamos hablando de sacar de boca hasta todo y está mucho. Entonces, eso lo utilizan también con computación de geofísica. No solamente en exploración, sino en física de producción, que para guiar la exploración.
Yo lo primero que le dije,
un asesor que tiene 30 años, pero tiene 30 años haciendo cosas, pero ya quizás tiene una mentalidad muy vieja.
Además era más fácil, era más superficial.
O sea, ese asesor le está pagando $10,000 en un mes, te pagan, bueno, $30,000 en mes, y a ti te pagan, no sé, te pagan un poco, ¿no? Y tú dices, ¿sabes qué? Yo tengo esta idea, o sea, vamos a hacer así, o sea, pero viene y se levanta el asesor y le dice, ¿sabes qué? No, considero que esta persona tiene que hay que hacerlo así, porque así lo hemos hecho durante 30 años. Aquí hay que hacerlo. Porque así pasaba, por ejemplo, cuando llegamos nosotros le aportaron un asesor, un señor que tenía 76 años. El tipo era muy bueno, o sea, tenía una metodología para explicarte cosas como que, entiendo. Pero cuando él venía con nuevas tecnologías, el tipo decía, no las creía, muchas veces nosotros tomamos decisiones erradas, porque al momento que nosotros trabajamos los oficios contra el asesor, pensando, no, vamos a sacar los boxes, vamos a hacer esto, de esta forma, para utilizar la competencia. No se lo hacía así de mucho con la vida. Y entonces, al final, cuando se tomó la decisión, no se hace caso al médico de 76 años que no caminaba. Por ejemplo,
eso de la petrolera,
por ejemplo, había una
porque yo creo que hay mucho más desarrollo porque hay más reducido a información o a ver la muestra que sacan de los modos. Y sobre todo temas muy complicados sobre cómo mantener el pozo que no se reproducir.
Sorry, that was writing you an email to just to get in contact for sending the paper later. So the scientists.
Perfect.
Oh, yeah, sure. Oh, okay. Oh, okay.
Jack, what time do you wish to be done? I think we can just play it by ear. 'Cause I think they're pretty good. Yeah, so
I think we should be out. We're scheduled to go 10 to 6. Okay. So just play it by ear. Don't rush things.
Okay, so what I wanted to show everyone here is what we've got started through GeoSci and with SimPeg. So GeoSci is our main sort of like landing page for a lot of the resources that we're trying to develop at UBC and elsewhere. Actually, there's other contributions that have been added to this, and that's something we're very excited about. Sort of adopting a lot of these open source strategies of having multiple contributors and people bringing different expertise to the table. So the first site where you can basically find all of the resources is GeoSci.xyz. And so when you type that in, this is where you'll land. And so each of these is basically its own resource. So we've shown you this site, the DISC 2017. So that's where you can go and download all of the slides and find access to the apps and the blog for the DISC and sort of read about other locations and what's happened around the rest of the world. The GPG. So the GPG and EM are basically like web-based textbooks. So they're meant to be resources that are alive, that can be edited and fixed and have contributions added to them. The GPG is an introductory level geophysics resource. So it's a once-over lightly of all of the geophysical methods. We use it at UBC for an undergraduate geophysics course that's taken mostly by geologists and geologic engineers. So they're not geophysicists themselves. So it's not very equation heavy, more picture heavy and trying to show and give you a bit of an overview of all of the methods. So this is probably the most mature out of the textbooks that we have. The EM resource, I'll take you to this here quickly. This is the one that's been developed and motivated by this course. So this really is on electromagnetics. It's much more in-depth than what you'll find on the GPG. So it's just loading here, and it's a little slow. So when you go to EM GeoSci, this is what you'll see here. And so, as I said, this is really a web-based textbook, and so it can be edited. So if you come across a typo, you can come here and come suggest a fix, and we'll see that and get your contribution in. There's a couple things that I want to show you. One place that is really tailored for contributions is the case histories, and so these are all examples, field examples, and some synthetic examples that have been broken down into a 7-step framework and give you an overview of the geophysics done at a site. So quite a number of the case histories that you saw yesterday are up on here. So if you want a review of those, you can certainly see them here. So if we look at something like Mount Isa, for example, you can see that it's broken down into the 7 steps that we've been using throughout. And so if you have a case history that you think would be ideal to showcase here, please get in touch and we can work with you to get that onto the web. The way that this is sort of structured is this is like a once-over lightly, and then there's typically a standalone publication that contains all of the details. So most of these case histories that you'll see here actually have a publication associated with them. The other things that I want to show you, so we walk through everything from physical properties, the fundamentals, and one of the cool things about having this be on the web and interfacing to a lot of these open source tools is that there's figures that you can actually download the code and see how we created them. So I want to show you, just trying to remember where it is. I think it should be here. So there's examples like this where we're talking through a conducting sphere and a uniform electric field. And so if you come on this page, I'll show you, for example, the potentials. So we're looking at the potential for just a uniform electric field. We haven't stuck the sphere in there yet. But here there's actually the source code. So you can go and you can actually look and see how this figure was programmed up. And so if we click on here, that'll actually pop up and you can see step by step how that was created. So there's a few of those around. Not all of the figures are like that. So if there is actually a figure that you come across and you're like, hey, how did you guys generate that? Just shoot us a message and we'll make sure that that code gets up there. And so speaking of code, the page that I want to show you now is the apps page. And so I mentioned this briefly earlier, but what we have is there's really two styles of apps. So there's the first one that we saw yesterday, which are these EM apps. And these are really built to be sort of very quick to interaction. So it's a figure with slide bars for the physics. And that's what it is it's meant to be a tool to investigate the physics. The simulation notebooks are really meant to be, if you actually want to see step by step, how do you code up and solve a forward problem for frequency domain? There's an example of how to do that. So here we show you all of the code. Here we really don't show you any of the code. So that's sort of the two different scopes of those. So I'll show you the EM apps quickly and just how you can actually run these. So we have them hosted in a couple places. If you're comfortable with Git and GitHub and setting up your own Python environment, you can download them. But what I recommend for most people is you use Microsoft Azure. And so this is actually hosted on the web. It's a service provided by Microsoft that they allow you to actually run Jupyter notebooks live on the web. So they've got clusters around where we can actually just spin up some computations. So if you click on that link, it'll take you here. And so here you can sort of flip through and see all of the apps that we have. What we've tried to do is organize them so that the first name there is the method. So you can see these are DC examples. But if you flip over to the next page, you'll see there's some frequency domain EM. There's an example of marine CSEM on like that movie that we showed yesterday with the airwave. There's an MT example and then some time domain EM examples. So if you actually want to run these, you have to first create a Microsoft account. It is free, so there shouldn't be too many issues with that. So we'll just sign in here. So then right now this run button is still grayed out. So what we actually have to do is we'll make our own copy of this library. And so what's kind of nice about that is that you'll actually preserve your own copy of the notebooks. And so if you did want to make notes in them for yourself, those will persist and be associated with your account. And so here I get this little pop-up because Doug's already cloned this this library and this set of notebooks. It says, hey, do you want to overwrite that? And so we will. We'll make sure that we've got the most recent version. And so now we get our live run button, so we're good to go. So we can pick any one of these examples. Let's maybe look at the DC layer cylinder. So right now, when we click on that button, it's spinning up a server for us somewhere on the cloud, and we'll get access to be able to run this Jupyter notebook. How many of you have heard of Jupyter? Anybody? Okay, cool. Have you guys used it before? Yeah. Yeah, so this is, this is how I work day to day, is in Jupyter Notebooks. If you haven't seen it, it's an interactive computing environment. Most people interface to it first through Python, because that's sort of where it's most commonly used, but it is actually language agnostic. You can plug in a whole bunch of different types of programming languages to it. So for these apps, there's a couple ways you can run them, but what I would just say if you just want to run the app is do cell run all. And so it's going to then run each of these cells of code just all at once. And so the first thing that we're doing, can you guys see that text at the back? That's okay? So the first thing that we're doing is just installing some libraries. And so this EM examples library, that was written by us to build all of these figures. So it relies on SymPeg, which I'll show you in a minute. SymPeg is really the simulation and inversion engine. That contains all the code to run simulations and inversions. Whereas the EM examples is just kind of a wrapper on that, and it generates the figures that we want to show for these apps. So it looks like our kernel died. Periodically, that does happen. If you get a bad machine, it just doesn't make it through. So we'll try again. Okay, let's try. The way I'm running it now is just Shift-Enter. So that runs it each cell individually. Okay, I will run them locally. So we also have a copy on Doug's laptop, because sometimes if the internet connection isn't great, those types of things happen. So when you go and run those notebooks, do cell run all here. What we try and do in each notebook is give you a bit of a statement of purpose. So why did we create this? What are the important concepts that are in it? We describe the setup as well as what all of the parameters mean. Because sometimes the slide bars, people use a bit of shorthand notation. So we do actually describe what's there. And then usually there's a couple questions to sort of drive some investigation if you want to have a look at those. So here's one where you can go ahead and again look at that example that we showed yesterday of the shielding problem. So what happens if you have a very resistive or a conductive layer? So let's make our layer conductive. So we'll see what the model updates to. So now we've got a more resistive background in this conductive layer. And then you can flip and look through at the current density and see here that, for example, for a conductive layer, we get a concentration of current through there. You can also play around with different survey types. So if you want to do pole, dipole, dipole, pole, and then potentials, electric fields, charges, sensitivities. So there's a lot that you can interact with here. The second style of notebooks that I would like to show you are these, the simulation notebooks. And so there's less of these because they do actually take longer to develop in some ways. It's because we're trying to explain to you step by step what the code is doing. And so again, these are on GitHub or on Microsoft. So we can run these on Microsoft. I'll make a copy. So there's a few different examples. There are ones showing, do you remember the frequency domain sounding over a sphere where we had a cylindrical mesh? So if you want to actually go and like reproduce those figures from the slides, this code will show you how to do that. And then we also have one for time domain. So you can look at both of those and see those results. all of the SimPeg code, there's 2 papers about SimPeg. So there's one that Rowan Cockett is lead author on, and that describes really the SimPeg framework and sort of overall structure. And then there's one that I'm lead author on, and we published that just this past year. And that really describes the electromagnetics structure and a lot of our thought processes around how it's organized and all of that. So before, I think I'm going to introduce you briefly to SimPeg, and then we'll jump back to those simulation notebooks. So SimPeg is this button here. So SimPeg stands for Simulation and Parameter Estimation in Geophysics. It is an open source project, so you're free to use the code, adapt the code however you like, as long as it's referenced. And so it's up on GitHub, and there's a few different ways you can interact with us in terms of, we've got a Google group and a Slack channel. I'll show you how to find those. So there's a few different things you can look at with this site. There's a bit of a statement of motivation of why we've been developing this, a link to the paper, and then I want to take you here to the documentation. So 2 important things to point out to you on this front page here. This Google group is really meant to be a place where you can come ask questions. You know, if you have a DC forward simulation that you want to set up and we don't have an example that answers all your questions, this is a place to go. So anytime you write something there, an email will be sent to everybody who develops SimPeg and a lot of the users who are interested in being a part of all of those conversations. The other link to have a look at, there's a link for Slack. And so this is actually like a chat environment, basically. So you can come and interact with us more so in real time. And so both of those are good resources in addition to the documentation. And so what I recommend actually starting with when you land on the docs is really the examples. This gives you a bit of an overview of what's there. And you know, it gets you up and running with something right away. So at the top here, we've got a few examples that are in publications. So these are all from the EM paper that we recently published. So if you want to actually go in and see how we made any of those figures, you can download and run any of this code. We've got some examples that show just a simple linear inverse problem. This one here, this is the, we show different regularization types. So you can compare what happens if you're looking for a smooth model versus a sparse model, just on this simple example. So this is a really powerful example for getting a handle on inverse problems. There's a few examples on how to set up a mesh. So a lot of codes, and often a really good place to start is just a simple tensor mesh. You can get up and running with it pretty quickly. But there are other fancier meshes, like looking at octree or curvilinear meshes and things like that. Then we get into the methods. So here's the Laguna de Mal inversion that Craig Miller did. And so if you actually want to go and rerun his inversion, we have it, he's posted it as an example. Then there's a few examples of magnetics as well. So you can go in and see how we run the linear inversion. So if that's something that you want to compare inversion results with, this might be a good starting point for you. And this one also shows, like, again, a couple different norms. So if you are interested in seeing, you know, a smooth inversion versus trying to do something that's a little more sparse, you can have a look at that. There's some examples for DC resistivity. And we're working on getting a 3D DC resistivity example in there. There's some in-house at UBC, they just haven't been cleaned up and posted yet. There's a few for frequency domain EM, for MT, and I'm going to show you shortly. We've got a tutorial on MT. There's time domain EM. There's some examples with Richard's equation for Veda zone flow. So for people who are interested in potentially coupling geophysics and fluid flow, that's been a big motivating factor for some of the development. And then there's a little bit with seismic, just straight ray tomography. So seismic is something we'd be interested in expanding to. So if you're interested in coding some of that up, you're welcome to join. And so as I said, it really is, it's meant to be a collaborative project. We're trying to be in touch and open to new contributions and all of that. So if there's something that you want to add as a utility or something like that, we're very excited about having people contribute. Okay, so then the next thing I'm going to show you is actually some of these simulation notebooks, which are built on top of SimPeg, and we'll have a look at some of the code there. So that brings us back here. So what I want to do is walk through these MT tutorial notebooks. So there are five notebooks here, and these were published really as a leading edge tutorial with the SEG. Have you guys seen, has anybody seen the leading edge tutorials? Yeah, one or two? If you haven't seen them, they're a great resource. So they're the only sort of default open access publication that the SEG does. And each one of them is sort of like a 2-page write-up with Jupyter notebooks or code examples with them. So they walk through anything from, in this case, doing an MT inversion. There's some that are doing, processing well logs and things like that. So they're a nice practical resource. So in this one, what we do is we're actually going to go basically end to end. So starting with the continuous MT equations, we're going to go through, discretize them, solve them, compare those to an analytic. So first we'll get our forward problem, right? Then we're going to actually do a couple investigations looking at important things in forward modeling, like your mesh design. And then finally, we get into the inversion and looking at some of the important parameters in the inversion. So I'll walk through this probably pretty quickly because there's a lot here. And so I encourage you to take a look afterwards and get in touch if there are pieces that you have questions about. So this is also a good example if you want to sort of get a feel for how SimPeg works, because we start, installing SimPeg and building this up from there. So here we're starting with Maxwell's equations. So we start from the 3D continuous Maxwell's equations, and we're going to discretize these in 1D. So all I'm doing here in this first step, if you're familiar with Python, you'll recognize a lot of these libraries. They're very standard scientific Python libraries. So NumPy is basically like MATLAB. It does all of your matrix calculations. SciPy, sparse matrices. And then there's some constants that we're importing and some plotting. Okay, so we start from the basic definition of the MT problem. So we got a current sheet, and so we're dealing with plane waves here. And because we've got a layered Earth, we can reduce this to a 1D problem. And we're going to set our boundary conditions. So we have a source up top, and then we're going to assume that by the bottom of our mesh, our fields have decayed. So here we walk you through, this is a finite difference approach. So we walk you through where all of the different things live. So where do your electric and magnetic fields live? Where do physical properties live? And then what does that mean once we're dealing with a discrete equation? So we get you here to now, what is our matrix system that we're going to solve? Okay, so with some of that background theory, we're just going to set up an example problem. And one of the things that we want to have handy is the skin depth, because that's going to inform how we actually design our mesh. So what do you think? So I printed two values here, the minimum skin depth and the maximum skin depth. Why are those important for mesh design? If you you're quick, you read the answer. What does the minimum skin depth tell us in terms of what we should be doing with our mesh?
This depends on the frequency you choose to measure the transfer function. The first skin depth may be the high frequency. This is your first dip in your sound, the MT sound, and the last skin depth is the lower frequency. So do you do this different skin depth to estimate the different dip in your transfer function and then your results are final?
Okay, and so you're right that it's with the highest frequency is the smallest skin depth and the lowest is the deepest.
Yeah, I think small set up the right match, right? In order to the lowest and largest element that you need to resolve.
So okay, so if we take the minimum skin depth, what decision am I going to make based on that?
So at least 158 will solve that.
Okay, so in terms of, if I'm going to set up a mesh, I'm going to discretize my world. What exactly? Okay, so looking at the spacing, right? And so we want to make sure that we've got a few cells that are smaller than this near the surface, so that because this is telling us how quickly the fields are changing. So we need to make sure that if we're wanting to model the physics, that we've got enough cells to really capture how quickly that's changing. What does this one tell us? The maximum skin depth.
The size of the mesh.
Mm-hmm. Right, because we need to make sure it goes far enough, because we've said at the bottom the fields have decayed. So if we make our mesh too short, the fields won't have decayed. And so we'll actually show in the next example one of the impacts of this. So exactly. So what we do here for setting up this first mesh is we choose a minimum cell size that's 4 times smaller than our minimum skin depth, and make sure that our padding extends at least 2 times the maximum skin depth. So in this case, all we do is then plot up the mesh, and we print out again how far did we want to extend, so we can make sure that when we plot it up, it's going far enough. And then here we print some details. This is an important thing to look at if you're going to set up, for example, a 3D problem especially, because you need to know how many cells you have, because that's going to control how long the computation takes. So all I'm doing here is defining the model. So we're going to put a model on a mesh. Since it's a half-space model, it's not overly interesting to look at. It's just a straight line. And then we define some frequencies. So now we've defined basically all the parameters that are setting up the Ford simulation. Okay, so that gives us everything that we need to actually construct our matrix system. So that's what we do in this next step. We've defined what it should look like in theory, and then we actually show you what that looks like in code. So you can compare basically this A matrix, which is a grad, an I omega mu, an M sigma, and a divergence with this guy here. And then here we go ahead and actually solve that. So I think they may have throttled the... So I'm just going to update this because we seem to be having trouble with the Azure machine. Okay. Okay, I will just download it because I don't remember where it is. Okay. Sorry about this. Okay. Okay, so now we're back. So from here, we actually went and solved that matrix system, so now we get our fields. And from there, we can go ahead and calculate impedances, which are actually going to be our data. And then at the end of this notebook, all we do is just a couple simple sanity checks. So we know that for a half space, our phase should be 45 degrees. And our parent resistivity should be equal to the true resistivity. And so those are a couple things we can simply check. And then the final thing that we do is actually set this up basically as a function. So we've gone through it step by step and outlined all of the steps, but now we actually want to reuse that forward simulation. So we show you how to combine all that. So then the next notebook, what we do is we're going to actually explore a couple important decisions in setting up a forward simulation and before you actually get to an inversion. So here, because Doug didn't have this, we're just downloading the code that was published with the leading edge tutorial. So that's now there. And then again, we're going to set up a simple model, but this case, we're going to actually put a target in. So we go through a lot of the same steps with defining the mesh. We set that up. Okay, so then in this case, what we have is we've got basically a half space with a single conductive layer in it. And then the first thing that we're going to do is actually compare this to an analytic. This serves a couple purposes. So first, we've done a good job discretizing. So we know that we should actually be able to model this pretty well. So we should match the analytic. And in this case, we're looking at apparent resistivity in phase. We're doing a good job. So the next thing that we can actually do is use the comparison with the analytic as a tool for mesh design. So let's actually start, pushing some of the boundaries on our forward simulation and see where we start to break down. So what we've done here is created a small little widget to examine mesh design. So if you're, I don't know, for those of you who use Jupyter, have you seen the IPy widgets library before? No? This is worth checking out because all it does is basically wraps a function and puts slide bars on it. So all we did to generate this app is basically say, I want a slide bar called domain extent. I want something for my cell sizes. And then this is the function that should take it. So this is a really valuable tool. I use it actually a lot when just flipping through simulation results or want to scroll through a 3D model or something like that. It's a really handy, quick tool.
Sorry, is that based on Qt?
I think it might be. I don't actually know. Yeah. It's all out of the Jupyter team, so all the code is online. So in this example, we've got two things that we're going to play with. So we got our minimum cell size and our domain extent. So let's start with the minimum cell size. Right now we're at 125 meters. what's going to happen if I start to increase that? Where's it going to break down? If we have high frequencies here and low frequencies here, where's our solution going to break down?
You're increasing the cell size, right?
Yeah.
The high frequency.
So let's take a look. So you can see, especially here, especially in the phase, we start peeling off the analytic at the high frequencies. We also start peeling off a bit in the conductor as well, because there's things changing quickly in there. Okay, so let's bring that back. And then what about this guy, the domain extent? So if we start to bring that up, you can see we pretty quickly start peeling off the analytic at low frequencies. So that gives you a bit of an impact, a bit of an idea of what your boundary conditions are doing. And if you wanted to do something like this in 3D and play around with your padding extent laterally as well, that could be a good example. So the next thing that we look at in this example is really a classic example of non-uniqueness. So before you go ahead and actually approach an inversion, it's really important to understand and get a handle on what can you actually expect to pull out of your data. And so the classic example of that in magnetotellurics is the non-uniqueness due to the conductivity thickness product of a thin layer. So what we're going to do is we are going to compute the apparent resistivity in phase for 5 different models. So each of these we have a conductive unit, all with the same conductance, but different thickness and different conductivities. And so if you go ahead and compute the apparent resistivity in phase, I mean, in all of those, you see that we've got a conductive layer. Like we're aware that there is a conductor there. But if you add even a bit of noise to this, you'd be hard pressed to tell the difference. So this is a powerful example for showing that, you know, we can't uniquely resolve the Earth. And so unless you have a priori information that you can bring to the inverse problem, we can't necessarily tell you whether it's the blue model or the orange model. And to drive that home, this example just lets you add noise to your data. So here we can add noise, for example, to the apparent resistivity. So something like, you know, 8% noise, there's no way we're going to tell the difference between any of those with our data. Even less than that, probably 5 or 6. So then with those things in mind, we'll actually go now to the inverse problem. So I'm just going to download this one again so we don't run into issues here. All right, so in this example, I think we've already got that. We set up the inverse problem. And so the way that we typically define the inverse problem is we're going to pose it as an optimization problem. And so in that, we've got 2 terms. So this one here, call our data misfit. So that's a measure of how well our forward simulated data is matching our observed data. And that's going to include a noise model. And then phi-m is our regularization term. So that is basically how smooth our model is, how small our model is, or if you want to impose more geologic constraints or things like that. You can do that through here. And then in between the two, we have this beta term, which is the trade-off parameters. That tells you how well do I want to fit the data misfit versus the regularization. What do I trust more? And so in this notebook, we walk through basically each of these parameters and show you some of the impacts of those choices. So there's a lot more details here than we have time to go through, but hopefully it's a decent standalone write-up, and if not, you can get in touch. So in this example, we're going to use a 5-layer model. Sorry, I'm going through that quickly because it's all, again, setting up the mesh and defining the problem. So here we're using a 5-layer model. So we start with a resistive layer up top, get a little more conductive, and a resistor, another conductor, and then a bit more resistive in depth. So this is sort of designed to be a bit like a typical geothermal 1D section. And so the first thing that we do is generate some observed data. So this is all synthetic, so we're going to simulate some data and then add some noise to it. And then here we'll go ahead and plot it so you can see what it is that we are actually going to try and fit. So we've got our, this is a little small. So the black line is the clean data, and then the blue with the dots is the noisy data. So that's going to be what we're working with in the inversion. Here we walk through some of the pieces of the SimPeg framework. And so we outline like what each of these boxes, which is just a module, what each of them do. I won't go through that really here. But what we've done in this example is basically wrap that up so that each of the parameters that you want to play with is just an input to a simple function. And then this function does all of those SimPeg pieces. So you can see things like the data misfit and how we're assigning uncertainties, how we're setting up our regularization, the optimization, and go from there. So what we're going to show first is actually the changing of the beta parameter. So what happens when we do a good job fitting our regularization versus our data misfit. So we're going to run, I think there's something like 35 iterations where we just are basically starting with a high beta, and then we're just going to slowly lower it and see what happens. So one of the first things that you might want to look at is actually the Tikhonov curves. So these tell you what your data misfit is as a function of beta, what phi m is as a function of beta, and then the trade-off between them. The star that we've marked here is what we're calling our target misfit for this case. So we base that on if your noise is Gaussian, then it should be, your data misfit should be the same as your number of data. And so that's what we defined as our target misfit. But you can look at other things like L-curve, and if you look at a standard sort of inversion tutorial, you can compare all of those different choices. So then what we did to actually go through and look at these results is, again, set up a little widget. So here we're going to scroll through iteration, and you can see, so in this one, in this plot, we'll show you the model. So the black line is the true, and then the blue is going to be the inverted. We've got our apparent resistivity and phase, and then this is showing you the Tikhonov curve and where we fall on it. So the blue dot is the iteration. So here we're starting with a very high beta, and we're going to decrease that as we go. So as we scroll through, you can see that we start to introduce a bit of structure into the model. You can see we're starting to fit lower frequency trends in the data first, and then as we continue on, introduce more and more structure. And so here, this is where we've hit our target misfit. And so you can see we're doing a pretty good job showing that there are 5 distinct layers, 2 conductors. We've done fitting the data reasonably well. What do you think is going to happen if I keep pushing harder? If we up the iterations, which in this case we're going to drive beta further and further this way, reducing beta. Smooth? So the model will be more smooth. So if we're going to reduce beta. So we reduce the weight on our regularization. What do you think will happen?
That it's going to get unreal with the direct data.
Yeah, so if we keep upping it, the inversion starts to introduce more and more structure to try and fit all the details here. So in this case, we've got now a lot going on that isn't geologically reasonable. So we've introduced more than what makes sense. So this is the danger of overfitting your data. So in the publication, we showed 3 different iterations. One where we have underfit, one where we've hit the target misfit, and then one that's overfit, to give you a bit of an idea of what some of those impacts are. And so one thing to note, I mean, although we've marked the target misfit, that's not always something that is immediately evident, right? There's a lot of choices that went into defining that. You set up your noise model, so that's a choice that you made. We are choosing the different regularization parameters and all of that. So it's not necessary that you want to always choose exactly this model. You need to be looking at a few iterations around there to choose what makes most sense geologically and fits your data. So the next thing that we look at here is looking at the smallness and the smoothness weights. So we use S to say smallness, and here Z is the smoothness. So Z, alpha Z, the smoothness penalizes derivatives. So it says don't introduce large changes in my model or large gradients in my model. The smallness term, what that does is says stay close to a reference model. So at every pixel, it's going to try and push it towards the reference model. And so these are things that you can also tune in the inversion. And so here, we're going to actually look at what happens if you go to one extreme or the other. So while this is running, we're going to run a few different iterations for each. What do you expect to see if we have a smooth inversion here where we've got a large alpha Z and a small alpha S? What should our model look like? In both cases, we're going to fit the data to the target misfit. What do you expect both of those to look like? So if we have a large alpha Z, what should our model generally look like? Go for it.
Is high prejudice in the vertical derivatives of the wall.
Sorry, can you say it again?
It will prejudice the vertical derivatives of the wall, so you expect something sharp.
Okay, so we think this one will be sharp. Okay. And so then what will this one be? If we have a large alpha S.
If you increase the alpha, the result will be very much like your starting model or something like that.
Okay. Is there anybody else?
Can you
saying what's the difference?
Mhm.
First, alpha,
So the first one, sorry, that's probably a bit small.
that's to see if your next model is going to be similar to the first one.
So the alpha S, let me actually scroll. I'm just going to scroll to the top. We should have had this down here. I'll show you what the equation is. Okay, so I don't have to write at the top. Okay, so this is what we're defining for our regularization. This is what it looks like. So we've got our alpha S. So this whole term, we call this one the smallness, and then this is the smoothness. So alpha S here, if we turn up alpha S, it basically then tells us that we want to really minimize this term. We want that to be small because the optimization is going to try and minimize that. Whereas if we crank this up, then it's going to try and minimize gradients in your model. So what should it look like if I make, let's first make alpha Z really big. What do you expect the character of our model to look like?
Like your first solution, like really smooth.
Mm-hmm. And then if we crank this up,
You will be looking in space solution like two solutions that are really similar to your reference model.
okay.
Well, it depends on your model.
Yeah. So our reference model we're just going to use is 100 ohm meter half space. And then we're still with that same 5-layer model. So I'm going to scroll down and we'll show you what this looks like. So does everybody have a picture in your head? Okay. So this is what the 2 inversion results look like. So our smooth, you're right, it looked very much like what we had before. Smooth curves, right? We've said don't introduce large gradients. The small one, what's happened is we're trying to stay really close to 100 ohm meters. And so what it does is basically then cranks points up and down to try and keep everything else as close as it can to our reference model. So in this case, we get a really choppy model. So that can be the danger of really ignoring that smoothness term and putting too much weight on just the smallness on its own. But those are powerful places to introduce some a priori knowledge, and that's something that you can play around with here is changing your starting model, changing your reference model. For instance, if you did, a layered reference model or those kinds of things, you can play around and see what that does. So it was a pretty quick overview. There's 2 other notebooks that if you're really interested in drilling into simulations and inversions that you can look at. These are what we've called it as an appendix because there are a lot of details. But here we actually go in and derive the sensitivity. So if you want to see how do you actually figure out what the Jacobian should be for the MT problem, all of the details are there. And then in this one, we actually show how we test that. Because there are a lot of moving pieces when you're calculating sensitivities and adjoints. So how do you know at the end of the day that you did it right? And so that's in here. So yeah, are there questions with that or other things you'd like to see? No? Okay, then I'll just wrap up by showing you again. If you are looking to use SimPeg, looking to develop, please get in touch because there are resources here, but we know that it's not sufficient for you necessarily to get up off the ground with an involved problem. So the links again are here. There's a Google group and then Slack. And so both of those are resources, and we're very happy to have people in touch because your questions will hopefully serve eventually as a supplement to the documentation. So. Are there other things?
Nope.
Okay.
that wraps it up. Time for beer. Anyway, listen, thanks everybody for coming out. And yeah, we hope that maybe we spark some interest here about electromagnetics and developing open source stuff and getting kind of a community together to talk about problems and work on problems together. So yeah, with that, good luck. See you guys. Thanks.
Yeah. Yeah, it shouldn't be a problem. So Simpeg is up on
I use
yeah. So like I have Python and I find that as well. If you just can't install Simpeg, it should be fine. Yeah, so it's actually